Show by the principle of mathematical induction that for all n belonging to the set of natural numbers, where the following equation is true. Let us begin. So first what we'll do, we are going to convert the given equation into a statement. For this, we will suppose that let P of n be a statement. This is going to be a mathematical statement. P of n be a statement such that P of n will be expressed as, we'll take 1 multiplied to 3 added to 2 multiplied to 4 added to 3 multiplied to 5, going all the way up to the last term, which is n multiplied to n plus 2. And when we sum it up, it's giving us a result of 1 over 6 times n plus 1 times 2n plus 7. So we're going to name this as statement number 1, also referred to as the statement Pn. And we need to verify that this particular statement is true for all n belonging to the set of natural numbers by using the principle of mathematical induction. So what we have to do here is that we have to verify that this particular equation, or you can say the statement, is true for any natural number that we choose. So it does not matter what natural number, be it 1, 3, 5, be it 100, it has to be true for any natural number that we are going to pick up. So first what we'll do, we are going to verify that this is indeed a true statement for n equals to 1. So for n equals to 1, we will find out P of 1. So P of 1 simply means take the first term of the given equation. So we have 1.3. This is going to be equals to 1 over 6 times. So we have n times n plus 1 times 2n plus 1. We're going to replace that n with 1. So we have 1 multiplied to 1 plus 1, so that's 2, multiplied to 2 plus 7, so that's going to be 9. So 1 times 3, that's going to be equals to 3. Now 2 times 9, that's 18, and we have division by 6, so 18 divided by 6, that's going to be 3. Now since we're getting 3 equals to 3, this simply tells us that P of n, the statement P of n, is going to be a true statement if we choose n values to be equals to 1. So that means coming out to be true for n equals to 1. Fine. Now, in order to check whether if it is true for other natural numbers as well, so what we'll do, we're going to choose another natural number m. So for n equals to m, let us suppose that the statement P of m, this is a true statement. We're making an assumption here. This is a true statement. Fine. Now, if this is true, this simply means that we can now rewrite the statement P of m as, so we have 1 multiplied to 3 added to 2 multiplied to 4 added to 3 multiplied to 5. This goes all the way up to, now we had the original statement as n times n plus 2, but here we are going to replace n with m. So we have m multiplied to m plus 2. This is going to be equals to 1 over 6 multiplied to, so here we have n, but we're going to replace it with m, multiplied to m plus 1, multiplied to 2 times m plus 7. Fine. So let this be statement number 2. And we are supposing that this is a true statement. Fine. Now if a P of m is true, we will need to show that the next consecutive natural number that we pick up, which is m plus 1, so P of m plus 1 must be also true, to show that this is also true. In other words, what we have to do is that the statement P of m plus 1, which is going to be given by 1 multiplied to 3 plus 2 multiplied to 4, going all the way up to m times m plus 2. But since we're considering the next consecutive natural number, we have to replace m with m plus 1 to get the next natural number, which is m plus 1 multiplied to m plus 3. All we have done is replace the m with m plus 1. Now this is going to be equals to 1 over 6. So we have to replace the m on the right hand side as well. So m was going to become m plus 1 multiplied to m plus 2 multiplied to, so replacing 2m plus the m in 2m plus 1 with m, that's going to give us 2 times m plus 3. Okay, so here this is what we need to show. So what we'll do, we'll start from the left hand side. So what we have on the left hand side is this particular expression, 1 multiplied to 3 plus 2 multiplied to 4, going all the way up to m times m plus 1 added to m plus 1 times m plus 3. Fine. Now, luckily for us, the sum of the first term all the way up to the second last term, we can replace it with this particular expression, 1 over 6 times m plus 1 times 2m plus 7. And why can we do that? That's because we have already assumed Pm to be a true statement. So since Pm is a true statement, now we have this 1 over 6 multiplied to m plus 1 multiplied to 2m plus 7. And to it, we are going to add m plus 1 multiplied to m plus 3. Fine. We have to combine them. So let's do one thing. Let's take m plus 1 divided by 6 as the common factor, which means that we now are left with 2 times m squared plus 7m added to, we have taken out m plus 1 as the common factor and also 6 as the 1 over 6 as the common factor. We have 6m plus 18. Fine. So let's further simplify. We have m plus 1 over 6 multiplied to 2 times m squared plus 13m added to 18. Fine. Okay. Now we have m plus 1 over 6 multiplied to, so 2m squared plus 13m plus 18, we need to factorize this. That's going to give us m plus 2 multiplied to 2 times m plus 9. Fine. So that's going to be equals to, now we have m plus 1 over 6 multiplied to m plus 2. We're going to rewrite 2 times m plus 9 as, so what we'll do, we'll take 2 multiplied to m plus 1 added to 7. And this is exactly the expression on the right hand side. So we can compare it. Yeah. So here I've made it a mistake here. So 2m plus 7. So when we replace this m with m plus 1, so this is going to become 2m plus 9, not 2m plus 3. Okay, so that's exactly what we have obtained here. Hence, here we have obtained, so let's write it out, since the left hand side of the expression equals the right hand side, this is simply telling us that the statement P of m plus 1 is a true statement. So P of m comes out to be true. Now if this is true, hence we can now generalize it. We can generalize and say that P of n is true. The P of n is going to be a true statement for all values of n. For all values of n belonging to the set of natural numbers n. Hence we have successfully verified that the given statement is true by using the principle of mathematical induction.